it too. So this is their very first time taking physics is the AP course, which is a brutal way to go. But oh well. All right, so here we go, the big review. We started off with linear motion. You guys have three equations in your reference sheet, which look something like this. The first one is, I'm going to write it in a slightly different form, but basically the position of an object is equal to its starting position plus its initial velocity times the time, plus 1/2 the acceleration times the time squared. And that's probably the most important equation. It tells you a couple of important things. The first important thing it tells you is that if there is no initial velocity, so if the initial velocity equals 0, then the distance an object travels, delta x, is proportional to the time squared. That's the first big concept you have to understand. If there's no initial velocity, something starts from rest, then how far it goes depends on the time squared if it's accelerating. Okay? If it's not accelerating, the distance is proportional to the time. If it's accelerating, the distance is proportional to time squared. The reason you got to know that is when you get those experimental design questions and they say, what will you plot? If you're trying to find acceleration, you have distance and time. Don't try to do calculus and intervals and stuff. It's really complicated. Just plot distance versus time squared. You'll get a straight line. The slope will be half the acceleration. Okay? The other equations in there are somewhat useful. For example, the final velocity at the end of an interval squared is equal to the velocity at the beginning of the interval squared plus 2 times the acceleration times delta x. And I think the third equation on there tells you the final velocity equals the initial velocity plus the acceleration times the time. Okay? You will be asked to solve only problems where the acceleration is constant, but you will be asked conceptual questions about whether the acceleration is constant or not. Okay? So one way to help sort things out like that are with graphs. So the first important graph you have to know is that if we give you a graph showing you the position of an object versus time, if the position of an object versus time looks like this, for example, what is the slope telling you? Velocity. The slope is the velocity. So that's one thing you got to know with the graph. Okay? If you have distance versus time, the slope is the velocity. What is happening to the velocity in this case? Is the velocity increasing or decreasing as time goes by?
Decreasing.
It's decreasing. Therefore, the acceleration is negative. If you're in calculus, you know the acceleration is the concavity of this graph. So the slope is the acceleration, the velocity, the concavity is the acceleration. If you're not in calculus, it's okay. Think about which way it's curving. The slope is decreasing, so the velocity is decreasing. Okay? The second important graph you have to know, and probably the most important one, is the velocity versus time graph. If the velocity of an object, for example, goes like this, what does the slope tell you? It's the acceleration. What does the area under the graph tell you? It's the displacement, right? So the area is the displacement. So if you're given a graph and you have velocity versus time, the area under the graph tells you the displacement. Now, quick reminder, what's the difference between displacement and distance? So displacement versus distance. So if I start right here and I go 2 meters this way and 2 meters back, what does my velocity versus time graph look like? So this is an example. I'll do an example on that. If I move 2 meters to the right and 2 meters to the left, what does my velocity graph look like? Let's assume I accelerated instantaneously.
The line is below the line.
My velocity looks like this. It was positive and then it was negative for equal amounts of time. What's the area under that graph? The area is 0, which means my displacement is 0, right? Which makes sense. If I started here and I went this way and I went that way, my total displacement is 0. I am where I started. Okay? So if you want to find the area under this graph, it tells you the displacement. What if I wanted to find the total distance I went?
The area under the absolute value.
That's right. Graph the absolute value of the velocity and find the area under it. Or just find all the areas geometrically and don't worry about whether they're positive or negative. Treat them all as positive and add them up. If I go 2 meters this way and 2 meters back, my distance is 4 meters. That's how far I've traveled. My displacement is 0. Okay? So that has to do with the vector nature of displacement. Okay? Okay, so that was, we spent the first unit just doing a bunch of problems like that. Things to watch out for, you got to be able to interpret the graphs. If you have a motorist speeding by at a constant velocity and they pass a police officer and the police officer starts to accelerate, and you want to know when does the police officer catch the motorist, on a graph they would catch the motorist when the police officer's distance versus time graph intersects the motorist's distance versus time graph. If you're solving algebraically, you would find when are they at the same place at the same time. So you'd have 2 equations, one for the motorist, one for the police officer, and 2 unknowns, D and T, and you'd solve 2 equations simultaneously for D and T. The AP does not care how you solve equations. If you state the 2 equations and you say, I graph them to find the numerical solution, that's acceptable. Okay? You can also say, you know, I did calculus, and you can do calculus, but you have to state the principles you're using. All right? Okay, so that was linear motion. We then broke that up. By the way, there was a special case of linear motion, and that is what we call free fall. So I'm going to sneak that in here. So free fall was when you had linear motion in the vertical direction, and you got a freebie, right? If it was on Earth, what was the freebie? The acceleration was negative g, or negative 10 meters per second squared. That's always true for free fall. If the acceleration is not negative 10, it's not free fall. If you are falling and there's a parachute attached to you and your acceleration is only negative 6 meters per second squared, you're not in free fall. Okay? So free fall by definition is the only force on you is gravity and your acceleration is negative 10.
On the AP example, we always use negative 10 rather than negative 9.81.
Correct. You can use either one. On free response, you'll get the credit either way. On multiple choice questions, they're written so that they've rounded to 2 significant figures. So using 10 will get you the answer, as will 9.87. All right, and then we had this whole thing of projectile motion, right? So in projectile motion, we basically had linear motion, but it was going on in 2 directions at the same time. And the idea here with projectile motion was that the x and y are independent. They're independent. What's happening in the x direction, what's happening in the y direction, independent. The most important problem with projectile motion is knowing how long it takes a projectile to fall off a table if it's launched horizontally. By far the most important problem. So if you have a table and an object is rolling and it becomes a projectile, it's moving in the horizontal direction, its velocity in the y direction is 0, and so if you use this equation, delta y equals 1/2 a t squared. Since delta y is generally negative and a is negative, those cancel, and the height from which it falls equals 1/2 gt squared, which allows you to compute the time. We've done this lots of times. That's the most important projectile motion problem. If you're launched at any other angle, the initial velocity in the y direction is not 0. You'll have to factor in initial velocity in the y direction to find the time. Again, set up the equation using the formula and solve it numerically on your calculator if it's a difficult one. Okay? Completely valid. Here's the equation I'm solving. I solve it. You guys have seen enough rubrics to know you get very few points for numbers, right? You get 3 points for explaining and justifying and 1 point for calculating the answer. So, that's projectile motion. All right, on we go to dynamics. So that was 1 unit, that was the 2nd unit. Now we're on dynamics. So dynamics is basically the whole idea of forces, what cause motion. And we start off in dynamics with Newton's 3 laws. Which one's the most important?
4.
So what's Newton's first law?
Object in motion. Is that one?
Yeah. Say it the long way.
Object in motion stays in motion unless opposed by an unbalanced force.
And objects at rest
So they stay at rest.
unless an external force acts on them. And the straight line part, right? Okay, how do you say that the short way? It's called the law of inertia, but how do you say all that? Object in motion, stay in motion, objects at rest, maintain their state of rest unless acted on. There's an easy way to say that. If the external force equals 0, then A equals 0. Without any external forces, you can't accelerate an object. If it's sitting still, it'll stay still. If it's moving to the left, it'll stay moving to the left at the same speed. That's Newton's first law. Newton's second law is the big one. This one says that if there is an external force, you will have an acceleration. And how big that acceleration will be the ratio of the net force, the unbalanced force, to the mass. Okay? We generally write this as F equals ma, which is also correct, but you sort of lose the cause and effect there. It's forces that cause accelerations. The acceleration is inversely proportional to the mass. What was Newton's third law?
Equal and opposite.
What?
Equal and opposite reaction.
Reaction?
Force. Whatever.
Cheapers, that's so 7th grade. Forces come in
Pairs.
pairs. Mathematically, we could say the force on object 1 due to object 2 always equals the force on object 2 due to object 1, except one thing missing from this,
Negative.
the opposite direction. Okay? If the Earth pulls down on you with a force of 300 newtons, then if the Earth pulls down on you with a force of 300 newtons, then you pull up on the Earth with 300 newtons. Forces come in pairs. If the Earth pulls on the moon pulls on the Earth. You punch the wall punches you. And the forces are always equal in opposite directions. Now, if a bug hits a bus, which force is bigger? The force of the bus on the bug, the force of the bug on the bus, or are they equal? They're equal. What is not equal? The accelerations. The mass of the bus is so big that the force causes no noticeable acceleration. But the mass of the bug is so small that exact same force causes a huge acceleration. Right? So don't confuse accelerations with forces. Accelerations are the effects of the force. Okay? And those depend on the mass. So those are Newton's 3 laws. We sort of collected an assortment of other forces as we went along with this. Some of the forces we looked at were the normal force. The normal force is an important force. It's perpendicular to a surface, right? We talked about the gravity force. The force due to gravity was m times g, although that's an approximation. We'll talk about that in a minute when we get to gravity. We talked about friction forces. So there's 2 kinds of friction forces. If you're moving, the friction force always equals mu sub k times the normal force. And if you're sitting still, the friction force is always less than or equal to the static friction coefficient times the normal force. So remember, if you're moving, you know what the friction force is. It's just mu times the normal force. If you're sitting still, though, you've got to be careful. I can almost guarantee you there's going to be a problem, something like this. A box weighs 200 newtons. The coefficient of friction is 0.25. The coefficient of static friction is 0.25. So what's the friction force? If gravity is pulling down, if the normal force and gravity are equal, and they're 200 newtons, and the friction force is mu sub s is 0.25, what's the friction force? It's always less than or equal to 50. So if I apply a force of 40 newtons to the right, what does the box push back with? 40 newtons. Static friction always opposes attempts to make it move up to the limit. So what is the acceleration of the box if I push on it with 40 newtons of force? It's 0. 40 newtons is not enough to make it move. Okay, does that make sense? So just remember there's two kinds of friction. On your reference sheet, they group those as a single equation. They omit the subscript and they say less than or equal to. They leave it to you to figure out which one's which. Okay? Other forces we've encountered, the force that a spring exerts on a system is K, the spring constant, times its displacement from equilibrium. And the spring's force always opposes displacements from equilibrium, right? So we talked about that. So those are some forces we picked up. There are 3 important applications we got to look at. The first important application, so read those applications here. So here's some apps. The first one was what we called statics. So statics were those problems where nothing was moving. So as an example, suppose you have a traffic light, gravity's pulling down on it with a force of mg. There's a tension going this way, T1. There's a tension going this way, T2. And this is some angle theta, right? If it's in static equilibrium, what's the acceleration? It's 0. There's no acceleration, which means when you apply Newton's laws, the sum of all the forces, the unbalanced forces, must equal 0. This is a vector equation, which means it's true in the x direction, and it must be true in the y direction. The forces must be balanced horizontally and vertically, and that allows you to set up a system of equations. Horizontally, you would have T1, how much? What component of T1 is going horizontally? T1 cosine theta minus T2 equals 0. And vertically, in this case, you would have mg, or you have T sine theta, T1 sine theta minus mg equals 0. And that'll give you 2 equations. You can solve for T1 and T2. Does that ring a bell? Remember that? That was the application to statics. All right. The second application was the inclined plane. This is the big one. So the inclined plane. So in this case, you have an object. It may or may not have friction. It's resting on a plane that's inclined at some angle theta. What you have to do is be able to draw a free body diagram of the forces on this. Let's assume there's friction for now. So the forces, there's a force of gravity going straight down. We call that mg. There's a normal force which is perpendicular to the surface. So the normal force goes this way. And friction force opposes the motion. If it's sliding down the ramp, then the friction force goes up the ramp. Call that F sub F. To solve this problem, it is easiest to cant your coordinate system a little bit. And we'll call the direction of motion the x direction. We'll call this the negative y direction. This angle here is theta. Do you see why? If not, just memorize it, but it's easy to think about. If this y is opposite the normal force, right? As the incline gets smaller and smaller and smaller and smaller, what happens to this angle right here? It gets smaller and smaller also, right? It tracks with the incline angle. That's what you can remember there. Okay, so in this case here, the block does not accelerate in this direction. That's why we made the direction of acceleration x. All the acceleration is in the x. So we can say the sum of the forces in the y direction must be 0. And that gives us the condition that the force in that direction, the positive y direction, the normal force, minus the component of gravity in this direction, which is mg cosine theta, must equal 0, because it does not accelerate in the y direction. Because we rigged it so the y direction was the direction it doesn't accelerate. That tells us that for an inclined plane, the normal force is mg cosine theta. And you probably are familiar enough with that, you maybe just can use that directly, okay? But that's where it comes from. If we add the forces in the x direction, we get the mass times the acceleration in the x direction. That gives us the equation, the force in the x direction is mg sine theta minus the friction force, which is mu times the normal force, which is mg cosine theta. That equals m times a, and that all simplifies to g sine theta minus mu g cosine theta equals the acceleration in the x direction. On the conceptual part of the exam, you'll probably be tested to see if you understand if there's no friction, the acceleration down an incline is equal to g sine theta. Okay? And that's fairly easy to remember because there's two limiting conditions. What is the sine of 0 degrees? 0, right? So if the incline was at 0 degrees flat, what would be the acceleration of a frictionless object put on it? It would be 0. So if you said g cosine theta, you know it's wrong, because cosine of theta is 1 for horizontal. Now, what if sine of theta was 90 degrees? What if this incline was made 90 degrees and you put something frictionless on it? What would it do? It would fall at 9.8 meters per second squared, g, right? And the sine of 90 degrees is 1. It falls at g. And if you got friction in there, that reduces the acceleration by this component. All right? So the inclined plane was an important application of dynamics. We spent a lot of time on that. We did some labs. If you have a block on an inclined plane and you start to raise the plane, it begins to slip, and you can use these conditions to figure out the coefficient of static friction. All right? All right. The third application was coupled systems. So coupled systems are systems that are connected together. So for example, if you have a big box, M1, you've got a little box sitting by it, M2, that's attached to a string to another box, M3, and it's pulled by a tractor with a force F. Let's assume there's no friction, okay? How do you find the tension in this string right here? Or how do you find the force that M2 exerts on M1? How do you answer all those questions? Well, if it's a coupled system, there's something important that is the same for everything. What is it? The acceleration. The acceleration is always the same for coupled systems. If the acceleration is not the same, it's not a coupled system. All right? So, to solve this problem, remember that A is the same for every component. So what you're going to do is you're going to look at the whole system. So the general strategy is 1, for the whole system, you're going to say the net force equals MA. What's the net force on this whole system if there's no friction? What's the only force on it? The whole thing. Joey, what's the whole force? What's the only force acting on that system? It's just F. So this gives you the only force F must equal the mass, which is M1 plus M2 plus M3 times its acceleration. So you look at the whole system to find the acceleration. And now you use the fact that the acceleration is the same for every part. So if you want to know what is the tension in this string right here, right? What would you look at? What is this string pulling? M1 and M2. So you would say that for M1 and M2, whatever tension is in this string pulling them, that has to equal the mass times the acceleration. You know the mass, M1 and M2. You know the acceleration. You can find the tension pulling on it, right? How would you find the force on little m2? Well, you know its mass. You know its acceleration. You can find the net force acting on it, the only force acting on it. And the force acting on 2 due to 1 is the same as the force on 1 due to 2, but in the opposite direction, right? So that was coupled systems, okay? And those can also happen in situations that look like this. You might have, for example, a block on a table with a pulley and a hanging mass. And you might have a massless pulley, so you don't need to worry about all those moments of inertia and stuff like that. But in this case, you could say that the tension in the string pulls on this block to the right, and it pulls here up. And so you can look at the whole system. So you can look at this block, you can look at that block, you can find the total mass, you can find the total force, which is just mg, and you can find the acceleration of it. And once you do the acceleration of the parts, you can find the tensions. For example, this one here, mg is pulling down. What force is pulling up if you know the net force? Because you know the mass, you know the acceleration, so you know the net force. So you can figure out how much tension is pulling up. Okay, if you know the acceleration of this block, you can figure out what tension is pulling on it. Okay, so those are the three big applications of dynamics, Newton's second law. Okay, statics, inclined plane, and coupled systems. And if they're really brutal, they might give you a problem where you have an inclined plane with a coupled systems problem. Okay, that might be like part D to separate the 5s from the 5 pluses or something. So it's possible, but probably not too likely. All right, moving on to momentum. So momentum, there's an easy definition for momentum. The equation in your book, in your reference sheet, says that momentum is defined as m times v, and it's a vector equation. So momentum is the product of mass times velocity. That's not so interesting. What we really care about is the impulse momentum theorem, which looks like this. The force acting for some time causes the momentum to change. This is the big idea in this unit, right there. Okay? The big idea in this unit was right here. If you have a force acting for some time, it causes the momentum of a system to change. If there's no external forces, the momentum of a system can't change. If the momentum of a system can't change, its center of mass cannot change what it's doing. So if you have those problems where you have, a guy in a boat and there's no external forces and the guy walks this way, then the boat's got to go that way because the combined center of mass cannot move if there's no external forces. Okay. This leads us to one of the important graphs. There's 3 important graphs you got to know. This one, if you graph the force versus the time, and the force is not constant. Let's say the force gets bigger and then it gets smaller. What does that graph tell you? Dylan? The area under this graph tells you the change in momentum. It tells you how much the momentum changes. Do you need the mass? You don't. The area under this graph is the change in momentum. You don't need the mass to figure out the change in momentum if you have the area under the graph. Okay? So in this case, the area equals the change in momentum of the system. Right? That's called the impulse momentum theorem. Sometimes we call this the impulse. That's the change in momentum. All right? So generally we use momentum when there are 2 or more systems interacting. There are 2 kinds of collisions. The rare kind, which we call what? Elastic. Means that KE is conserved. And the other one is the inelastic. And that one, KE, is not conserved. Okay? This one is the real collision in most of the world. Sometimes we can approximate a collision between 2 very hard objects that don't deform. We can approximate them as elastic, but in general, most collisions are inelastic. Kinetic energy is not conserved. But what is conserved? Momentum. And so the big application here is that if the external force on a system is 0, then the change in momentum of the system is 0. Momentum is conserved. Okay? So that means that if I have a collision, bam, the hit and stick, okay? This guy loses 5 units of momentum. Where does it go? This guy gains it. If this loses 5 units of momentum and there's no external forces, this guy gains it. The total changes in momentum for the system are 0. That's what it means to be conserved. Okay? Now here's an important application of that. If this comes along and it sticks, let's say it's going 10 miles an hour and it sticks and it's going 5, oops, let me do this. Equal mass. Sitting still, moving 10 miles an hour. Sticks, and now they're going 5 miles an hour. Okay? Miles an hour. Meters per second. They're each 1 kilogram. I make it look easy, but these are really heavy markers. Okay, 1 kilogram each. How much momentum did this guy lose? He went from 10 meters per second to 5 meters per second. He lost 5 units of momentum. So what does this have to do? It's got to gain 5 units of momentum. It's going to go 5 meters per second. So this guy's going 5, that guy's going 5, everything adds up, right? What happens though if this one's going 10 meters per second and it bounces back at 5? Because they're really hard now, they don't stick. What happens if this one rebounds? How much did its momentum change? And it went from 10 this way to 5 that way. How much did it change? 15. Which means this one's got to do what? If this guy lost 15, this guy's got to gain 15. So if they hit and rebound, this one actually goes faster than if they hit and stick. Right? So the idea is that the more they deform, the more they stick, the less momentum is transferred. A hard collision transfers more momentum. This guy goes faster if the bullet bounces off than if it hits and sticks. That's a conceptual idea that'll be used a lot. All right? So this idea here, the momentum is conserved, means that the final momentum after a collision is equal to the momentum before a collision if there's no external forces. Now be careful. Make sure there's no external forces. What if there's friction? Well, if there's a collision between 2 cars and it doesn't say there's no friction, you can argue that if the friction force isn't very big and the collision happens fast, the change in momentum of the system is very negligible. Okay? So that might be a conceptual question. But in general, we look at problems where there's no external forces. This is a vector equation. That means it's true in every direction. And so, for example, if you have an exploding shell, there's 3 parts. 1 part goes this way, and 1 part goes down. Which way does the 3rd part go? And why? Huh? Why?
Because it goes opposite the 2, and then you combine them. It goes.
1 part goes this way. Look, what's the momentum before the explosion? 0. So what is the momentum after the explosion? It's got to add up